Message passing in distributed systems. Message passing is a fundamental communication mechanism used in distributed and parallel systems, where multiple processes or nodes interact by sending and receiving messages instead of sharing a common memory. In this approach, each process works independently with its own local memory, and any coordination or data exchange happens explicitly through operations like send and receive. These messages travel over communication channels, which could be network links or inter-process connections. Message passing can be synchronous, meaning the sender waits until the receiver accepts the message, ensuring tight coordination, or asynchronous, where the sender continues execution without waiting, allowing higher concurrency. This mechanism is essential for maintaining data consistency, enabling parallel execution, and supporting scalable distributed applications, as it clearly defines how processes communicate and cooperate in the system. Message passing improves system reliability and fault isolation because the failure of one node does not directly affect the memory or execution of other nodes. Each process operates independently, so problems in one part of the system remain contained, making the overall system more robust. It also enhances scalability, as new nodes can be added without modifying the internal memory structure or operation of existing nodes. Because of these benefits, message passing is widely used in distributed applications such as client-server systems, cloud services, microservices architectures, and other networked applications. In these systems, reliable and controlled communication between independent components is essential, and message passing provides a clear, well-defined mechanism to coordinate processes while maintaining system stability and performance. This diagram shows message passing in distributed systems, where nodes communicate by sending messages instead of sharing memory. Node 1. Node 1 is an independent process that sends messages to other nodes. This arrow shows Node 1 sending a message to Node 2. Node 2. Node 2 receives the message and processes it independently. This arrow shows Node 2 forwarding a message to Node 3. Node 3. Node 3 receives messages and acts on the received data. This arrow shows Node 1 also communicating directly with Node 4. Node 4. Node 4 receives messages and participates in distributed communication. Diagonal arrows. The diagonal arrows represent simultaneous and bidirectional message exchange between nodes. Bottom arrow from Node 4 to Node 3. This arrow shows Node 4 sending a message to Node 3. Synchronous message passing. In synchronous message passing, the sender sends a message directly to the receiver. The sender then waits until the receiver receives the message. The communication happens through a communication channel. Once the receiver gets the message, it sends an acknowledgement back to the sender. Only after receiving this acknowledgement does the sender continue execution. This ensures that both sender and receiver are synchronized during communication. Synchronous message passing is a communication method where both the sender and the receiver must be ready at the same time. In this method, a message is sent directly from one sender process to a specific receiver process. This is called direct communication, because the sender specifies exactly who will receive the message. The method is blocking, which means the sender must wait until the receiver has successfully received the message before continuing. This ensures reliability, as every message sent is guaranteed to reach the receiver. However, it also creates tight coupling. Both the sender and the receiver need to be active simultaneously for the communication to occur. Synchronous message passing is often used in situations where coordination is critical, such as in real-time systems or financial transactions, where missing a message could cause serious problems. Asynchronous message passing. In asynchronous message passing, the sender sends the message to a queue instead of waiting for the receiver. The sender can continue its execution immediately without blocking. The receiver later retrieves the message from the queue whenever it is ready. This method allows the sender and receiver to operate independently, making the system more flexible and efficient. Asynchronous message passing is a method where the sender does not wait for the receiver to get the message. Instead, the sender continues its execution immediately after sending the message. This is called non-blocking communication, because the sender does not pause or stop while waiting. The sender and receiver are decoupled, meaning they do not need to be active at the same time. Messages are usually stored in a buffer or queue until the receiver is ready to process them. This ensures that no message is lost, even if the receiver is busy. Asynchronous message passing is flexible and supports high concurrency, allowing multiple processes to communicate efficiently. It improves overall system utilization and is commonly used in distributed systems, messaging applications, and real-time event processing. Unicast messaging. Unicast messaging is a one-to-one communication method. A message is sent from a single sender, or node, to a specific receiver node. Only the intended receiver gets the message. This type of communication is simple, direct, and ensures reliable delivery of messages between two nodes. Unicast messaging is a point-to-point communication method where a message is sent from one sender to one specific receiver in a network. It is called one-to-one communication because only a single receiver gets the message. The sender explicitly specifies the receiver, making it a direct form of communication. This ensures reliability, as the message is guaranteed to reach the intended receiver. Unicast messaging is highly targeted, which reduces unnecessary network traffic and ensures that information reaches exactly who it is meant for. It is commonly used in client-server applications, direct process communication, and situations where precise delivery of data is required. Because of its direct nature, Unicast is simple, reliable, and efficient for most one-to-one communication needs in networks. Multicast messaging. Multicast messaging is a one-to-many method. The sender, or source node, sends a message to multiple selected nodes at the same time. Only the members of the specified group receive the message. This approach is efficient because it avoids sending multiple separate messages and saves network bandwidth. It is commonly used in applications like group chats or video conferencing. Multicast messaging is a one-to-many communication method, where a message is sent from one sender to a specific group of receivers. It is called one-to-group communication because the message is delivered only to multiple selected receivers. This approach is efficient, as it saves bandwidth compared to sending multiple individual unicast messages. Only the members of the designated group receive the message, which makes it targeted and reduces unnecessary network traffic. Multicast messaging is commonly used in applications such as video conferencing, group chats, and collaborative tools, where the same information needs to reach multiple people at the same time. By sending a single message to a group, multicast ensures faster communication, better performance, and optimized use of network resources. Broadcast messaging. Broadcast messaging is a one-to-all method. The sender sends a message to every node in the network. No targeting is required, and all nodes automatically receive the message. Broadcast is useful for global announcements, network discovery, alerts, or system-wide notifications. This ensures that important information reaches every node simultaneously. Broadcast messaging is a one-to-all communication method, where a message is sent from one sender to every node in the network. It is called one-to-all communication because there is no targeting. The sender does not specify individual receivers. Every node automatically receives the message, making it useful for sharing information with all devices at once. This method is efficient for global information, such as system-wide announcements, alerts, or notifications. Broadcast messaging is commonly used in network discovery, sending alerts, and updating routing information. By reaching all nodes simultaneously, broadcast ensures that critical messages are delivered quickly and consistently across the entire network. TCP, Transmission Control Protocol. Block 1, Application to Application. Two applications want to communicate, like a browser and a server. TCP makes sure the connection is reliable. Block 2, TCP to TCP. TCP creates a connection using SYN and ACK messages. It controls data flow and makes sure all data is delivered correctly. Block 3, IP to IP. IP breaks the data into packets and sends them across the internet to the correct destination. Block 4. Network to network. The network layer physically transmits the data through cables, Wi-Fi, routers, and switches. User datagram protocol is a connectionless communication protocol that sends messages called datagrams without guaranteeing delivery, order, or error checking, making it fast and lightweight. Block 1. Application to application. Applications send data directly without setting up a connection. Block 2. UDP to UDP. UDP sends datagrams very fast but does not check if data is lost or received. Block 3. IP to IP. IP sends the UDP packets to the destination. Block 4. Network to network. The network layer transmits the packets physically. MQTT is a lightweight messaging protocol designed for fast, efficient, and reliable communication between devices in IoT networks. Block 1. Subscribers. Subscribers are devices or users who want to receive data. Block 2. MQTT broker, center box. The MQTT broker is the middle server that receives messages and distributes them to subscribers. Block 3. Publishers. Publishers are sensors or devices that send data to the broker. Publishers send data to the broker, and the broker forwards it to all subscribers. HTTP, Hypertext Transfer Protocol, is a protocol used for transferring and exchanging data over the web, enabling communication between web browsers and servers. Block 1. Web client/browser. The web client or browser sends a request, like opening a website. Block 2. Request arrow. The browser sends an HTTP request to the web server. Block 3. Web server. The web server processes the request and prepares the web page or data. Block 4. Response arrow. The server sends an HTTP response back to the browser. Message passing is a key concept in distributed systems because it enables communication between nodes without requiring shared memory. Even though nodes do not share a common memory space, they can exchange data reliably using messages. Another important advantage is fault isolation. If one node fails, it does not directly affect the execution of other nodes in the system, ensuring better reliability. Message passing also supports scalability. New nodes can be added easily without modifying the existing system structure, which allows the system to grow efficiently. Additionally, message passing plays a vital role in process synchronization. It helps coordinate actions and ensures that distributed processes work together in a consistent and orderly manner. Overall, message passing is essential for reliable, scalable, and synchronized distributed computing. Structured data exchange ensures that all communication in a distributed system happens in a controlled and well-defined manner using messages. This approach allows the system to operate reliably, even when individual nodes fail, providing better fault tolerance. By avoiding direct memory access, message passing improves security and gives better control over how data is shared between nodes. Additionally, message passing is well suited for distributed environments. It works efficiently across network-connected systems, even when nodes are geographically separated, ensuring consistent communication and coordination. Overall, structured message passing enhances reliability, security, and efficiency in distributed systems. Message passing in distributed systems comes with some important challenges. One major challenge is deadlocks. Deadlocks occur when processes wait indefinitely for messages from each other. For example, Process A may wait for a message from Process B, while Process B waits for a message from Process A. Avoiding deadlocks requires careful system design or specialized algorithms. Another challenge is synchronization issues. Sending and receiving processes must be properly synchronized to ensure correct communication. In synchronous message passing, the sender may block until the receiver gets the message, which can slow down the system. In asynchronous message passing, the sender continues without waiting, but this can lead to race conditions or problems with the order in which messages are processed. Managing these challenges is critical for building reliable distributed systems. Another important challenge in message passing is message ordering. Messages may arrive out of order due to network delays, and ensuring the correct sequence is critical for maintaining system consistency. Overhead is also a concern. Sending messages involves copying data, buffering, and managing network protocols. When messaging is frequent, this overhead can degrade overall system performance. Scalability issues also arise as the number of processes increases. With more nodes, communication overhead grows, and maintaining a consistent state across all processes becomes increasingly difficult. Addressing these challenges is essential for building reliable, efficient, and scalable distributed systems. Message passing has several important applications in distributed systems. One key application is inter-process communication, or IPC, where processes on the same or different machines exchange information. A common example is client-server applications, where requests and responses are sent as messages between processes. Another application is in distributed databases. Message passing is used to coordinate transactions across multiple database nodes, ensuring data consistency and maintaining atomicity in distributed operations. Remote procedure calls, or RPCs, are also based on message passing. In RPCs, processes can call procedures on remote systems using messages. This provides a simple abstraction for network communication, hiding the complexity of sending and receiving messages while enabling seamless interaction between distributed processes. Message passing is also widely used for load balancing. Processes exchange messages to distribute workload evenly across nodes in a cluster. For example, cloud servers communicate to avoid overloading a single node and ensure efficient performance. Another application is fault tolerance. Nodes send heartbeat messages to detect failures, enabling recovery and reconfiguration when processes or nodes crash. In IoT and sensor networks, devices communicate readings and control messages using lightweight message protocols such as MQTT or CoAP. Additionally, client-server and peer-to-peer applications rely on message passing. Web services, chat applications, multiplayer games, and P2P file sharing all use messages to exchange information reliably and efficiently.